And welcome back to the Flamethrower AI Machine Learning Engineer interview series. Now, in today's video, we're going to be talking about a really popular and common classification model called logistic regression, which if you've been in the field of machine learning for any length of time, you've probably run into logistic regression before, at least in some capacity. And because it's so common, it's really common that you'll also get asked about it in some way, shape, or form within the machine learning engineer interview. So going into the interview, it's really a good idea to have a solid understanding of this model, have all the major pieces and components sort of clear in your head, so that if the interviewer asks you to describe any part of the model, you'll be able to do that with ease. And that's what we're going to do today. So I found it's less likely overall in interviews, especially machine learning, engineering interviews, that you'll be asked to actually write out equations and derivations in depth. It is possible, depending on your interviewer, it can happen, but more likely what they'll have you do is just sort of run through the model as a broad, higher level overview, and maybe they'll ask you, some more in-depth questions about specific parts. So that's what we'll do today. We'll go over a higher level overview and, the key things that I think you need to know. So logistic regression is sort of the classification analog of linear regression. So in logistic regression, you have basically a response variable model as W transpose X. So that's like the same as you see in a linear model. But in order to get it to perform classification, you push that input into a sigmoid function. And the sigmoid function, we'll write it as a function of z, is defined as this formula. 1 over 1 plus e to the negative z. So the overall model then is you're going to model your class output, and actually let's give it a different name other than y, just to keep it distinct from the training data. So we'll call it hw of x here, and the w denotes that the model is parameterized by this weight vector w here. And the overall model is we're going to model that output as 1 over 1 plus e to the negative w transpose x. And if you think visually about what this is doing, well, it's taking your linear input in x and pushing it through the sigmoid function. And the sigmoid function, roughly speaking, looks like this S-shaped. And, actually that was a rather poor approximation of it. I'm not much of an artist here, but let me try again. So that's a little bit better. So you can see when it intersects 0 here, it gives you a value of around 0.5. And then as you go towards negative infinity here, the value of the sigmoid goes towards 0. And as your x goes towards positive infinity here, the value of your sigmoid goes towards 1. So this is a limiting behavior. And basically this output here is going to be a number between 0 and 1, right? So hw of x is going to be in this interval between 0 and 1. So what we're going to do is we're going to interpret hw of x to be the probability that y, so the true classification value of x, is equal to 0. So that's the first class. We'll just assume we have two classes into which x can fall, so it can be in C0 or C1, and then y is that label, 0 or 1. So this is going to be the probability that x is in C0, so the probability that the label y here is equal to 0. And then we can obviously find the probability that x is in class 1 as just 1 minus the probability that y is equal to 0. And I don't know why I wrote this. This is the probability that y equals 1. Okay, so that's the general setup of the logistic regression model. And in an interview they might ask you questions about that. So they might say, how does logistic regression differ from linear regression? You can say, well, it's basically a linear regression model fed through this sigmoid layer of sorts, and that gives you a probability that your output is going to be in one of the two classes to which it can belong. And so the sigmoid allows you to get a probability distribution over these two classes, C0 and C1. So that's a good high-level overview. And then after that, they'll probably start digging into the training process. So what loss function do you use to train logistic regression? And the answer is that you use what's called the cross entropy loss function. Okay? And the cross entropy loss function is super common in classification problems. It's not used only with logistic regression. You can use it all over the place. But this is sort of the most common place where you'll see it. And you can derive this cross entropy loss directly by applying maximum likelihood estimation to this problem. And if you're not familiar with maximum likelihood estimation, you can check out our other courses. I'll also make another video on it as part of the interview series. So we'll go into more depth on maximum likelihood estimation in another video if you're not yet familiar. But you can also do some reading on it, and it's just a way of estimating these parameter values W. And it's the standard way of training machine learning models. There are other ways as well, such as like MAP, which is maximum a posteriori, but MLE is sort of the gold standard and is the method that you try first when naively training a machine learning model. So if you do the maximum likelihood estimation derivation, which we do that in our main courses. So if you want more info on how to derive the equations, you can check out those videos. But all you'll have to describe in the interview is that you run MLE on this problem to get the cross entropy loss function. Now, to run maximum likelihood estimation, you need to define the likelihood function of the model. Right, and this implies making a choice of what your likelihood function is going to be. So for the problem of logistic regression, we model the likelihood, which is the probability of our data X. And it's over the whole training set, not an individual data point. So, all right, probability of D, that's the training set. Given our weights, this is what we call the likelihood function, and we model that as a Bernoulli likelihood. And you can look up this function. It's just a probability distribution function, and it models basically what we're trying to do here, which is get the probability that X is either in class 0 or in class 1. So if you perform maximum likelihood on this Bernoulli likelihood function, you end up with the cross entropy loss. And once you have the cross entropy loss, then you can train your model. So how do you train this model? Well, you can either use standard gradient-based optimizers like gradient descent. That's one way. And pretty much any problem where you have some sort of differentiable loss function, you'll be able to use gradient descent. So there are very few instances where gradient descent doesn't work for optimizing your model. So if for some reason you can't think of a way to train a model in the interview and you're kind of blanking out, throwing out gradient descent is a great way to get the ball rolling, because very rarely are you going to be wrong. The other way you can train this one is using Newton's method, actually. So if you remember Newton's method from calculus, it uses a ratio of the gradient of h with respect to the Hessian of h, so the second derivative of h, basically. And it uses this to determine the direction which to step in the optimization. And Newton's method is actually guaranteed. Well, both Newton's method and gradient descent are guaranteed to converge to the global optimum for logistic regression, because this cross-entropy loss function in this instance, with the logistic regression model, is convex. So that's a really important thing to have in your head when discussing logistic regression in an interview, is that the loss function is convex in this case, because that gives you a lot of really key guarantees on both the speed of convergence and the optimality of the solutions that you find. So that's sort of a tricky question for people who don't know logistic regression really well, who've maybe only glossed over the model. They often won't remember that logistic regression has a convex optimization problem. And so interviewers will throw that out there to see if you really know the details of this model. So either of these methods work, and particularly when you use Newton's method, the algorithm that they use in this specific instance, which uses the Newton's method update, is called IRLS, which stands for iteratively reweighted least squares. And it really bears a lot of resemblance to the closed form solution in the ordinary least squares linear regression model. So that's sort of where it gets the name from, and you're basically reweighting that update and performing it iteratively when you do the Newton's method optimization. And you can sort of see that you're kind of reweighting it by this Hessian here. So that's where the name comes from. So if they throw out IRLS, you'll know what they're talking about in the interview. And let me think. I think that those are sort of the main points to cover with logistic regression. You can also do, like with any model, you can do regularization with logistic regression. So you can either use L1 or L2 regularization if you so desire. So if you see that your model has really high variance, when training, you might want to throw in those types of regularization. And of course, those are equivalent to performing map estimation with either a Gaussian or Laplacian prior on your model's weights. And if that was all mumbo jumbo to you, don't worry, we'll have another video on map estimation, so that'll become a lot more clear. But that's the gist of it. And yeah, that's a really solid start for logistic regression. I think if you know all these key pieces of the model, you'll be set up to perform really well in the interview process on any question regarding logistic regression. So I hope that was helpful, and I'll see you in the next video of the Machine Learning Engineering interview series.